stress transformation. So now you are going to transform the stresses from one plane to other planes. Okay, to find on which plane the stress is maximum. Okay, so for that, I'll simply demonstrate an example how the stresses is going to be. First, take a specimen. Let's say it is mild steel I am taking. Now, if I apply uniaxial state of stress on both sides, something like this. Now tell me, just a second, I want a little bit elaborated. Guys, are you there?
Yes, sir.
Okay. Now, if I take a small portion of the specimen and if I ask you to draw the state of stress for this one, can you able to draw it? Guys. So what kind of stresses will act on this one? The small portion of the body, which I am cutting it from the same specimen. It's a small piece from that body. How the stress will act? Is it the same stress or it is different? Hey, it's a very basic one, what I am asking. Are you able to understand? Same stress. Okay. Now, what I will do? It's the same portion, but now I am cutting it at a different angle. Can you tell me what is the state of stress for this? Anyone? Is it going to be same or it is different? No one? Any random guesses? Is it same stress or it is a different stress? Okay. So if you think it is same, then you are absolutely wrong. Okay. First, draw this specimen. Just the blown up picture of this. Just so the state of stress will be something like this. Remember, so in the entire strength of materials, state of stress is very important. State of stress means what kind of stress is acting on the body. Then you have to represent in a tensor form. And I told you about the tensor notation. Did you remember that matrix? Guys, sigma xx, sigma yy, tau xy. Are you able to remember this? This is called state of stress. So every time if a problem is given to you, first thing is you should note about what is state of stress. If you are able to figure out what is state of stress at a point in a body, your problem is solved. Okay, we have to identify what kind of stresses acting. Then you can transform those stresses. Then you can find what is maxima, what is minima. Then I will show you in a while how to find maxima and minima. Is it okay? Now, if you ask me to draw as of now, what is state of stress at some angle? Observe this. Now it is oriented at some angle like this. It's the same part, but now I am cutting it at a different angle. Now the state of stress will look something like this. You have sigma yy, you have sigma xx, then you have shear stress also. That is the beauty of stress transformation. So in one plane, you'll be having only one stress. If you take the other plane, you may have different stresses. Okay. Are you thinking how it is possible? Yes. Draw the state of stress. Can I go ahead?
Yes.
So write a heading, state of stress at a point. Now, if I take any random body, something like this, now I am going to apply some loads or some force. Let's say this is my P3 and P4, P2, there's something like P1. So if I take some point inside the body, let's say somewhere around here, tell me how many planes can pass through this point, guys. How many planes can pass through that point? I hope you know what is a plane.
Infinite.
Infinite. Very good. If you see, I can one plane can go like this, like this. So infinite number of planes can pass through the same point. But if I ask you to find out state of stress in all those planes, is it possible to do analytically? Is it trivial to find out state of stress in all the infinite planes?
No, sir.
No. So for that, what we are going to do, we are going to find out where the maximum normal stress, where the maximum shear stress. Then we are going to name those planes as principal planes. Okay. So whatever the plane in which the maximum normal stress will act, those planes are called maximum principal plane. Okay. Similarly, wherever you have maximum shear stress, we'll call those planes as maximum shear planes. So based on that, we are trying to find out how the failure is going to happen. Let's say you have the maximum normal stress in that plane. So there is a tendency to failure. Okay, we are going to find out that. Just a second. Now let's say if I am going to call this as some AA plane, and let's say this is some BB plane. I'll show you the free body diagram of the cutout part. Let's say if I am making a plane, something like this. Now I will draw the free body diagram of this side. Observe this. Then we have a plane of A. Now tell me how the stresses will act on this plane. Come on. How the stresses will act. How many stresses will be there? First tell me. Two stresses, right? What is the first one? So every plane contains two stresses first. You should know that. What is the first stress? Just now I am talking about that.
Normal and shear.
Correct. So how the normal stress will act exactly perpendicular to the plane. Okay. And shear stress will act along the plane, or you can say tangential to the plane. So this is your sigma n. That means normal stress. And this is your shear stress term. Make a note of this. This is how you will draw the free body diagram. So this is your P1. This is your P2. Corresponding to AA plane. Let's say if I am cutting about BB plane. So how the stresses will act? Will it act in the similar fashion or it will act in a different fashion? Different, right?
Different
Agreed?
reason.
Because the normal stress will be in this direction now. and the shear stress will be something like this. So based on the different planes, the stress orientation is different. Are you able to understand this? Guys, everyone, can you able to figure it out? Can I continue?
Yes.
Okay. You right? The stresses sigma and tau shown in the above figure so shown in the above figure are not the maxima or the maximum, normal and shear stresses occur on planes that are inclined to the sides of the element okay. So those are not the maximum, normal and shear stresses, remember that. And those will occur on the planes that are inclined to the sides of the element. So it may happen, let's say in this plane, the maxima will occur in this plane corresponding to sigma n and tau. So for this case, the maximum can happen something like this, or maximum can happen something like this. We cannot say as of now because we don't have any formula for that to find on which plane the maxima or the minima happens. Okay, right now we just know, let's say you have a specimen, and if you take a part of the specimen and if it is distributed with uniaxial or whatever may be the stresses, okay, let's say most probably they will go for biaxial state of stress. Okay, biaxial state of stress means you'll be having two sides, sigma xx will be there and sigma yy will be there and tau xy will be there. Okay, are you getting me? So for that state of stress, we are going to find out where the maxima and minima is going to happen. Is the idea clear? In the entire chapter, we are going to roam around these two topics, maxima and minima. It's a very important topic. Please understand this. Is there any doubt so far?
Excuse me, sir.
If you have anything to ask, you can post now. Quick.
Excuse me,
Yeah.
sir. I want to clarify one thing.
Yeah. Go ahead.
So, in the beginning of the chapter, you took like one in the normal thing and then another specimen with the angle. So, if the angle changes, the plane changes, and that's why the state of stress is different.
Correct.
Yes.
If the angle changes, then the state of stress will change. Absolutely correct. I'll prove that in a while.
Yes, sir.
Okay. Is there anything else? Can I continue, guys?
Yes, sir.
No. So, right. This is a kind of definition only. The state of stress at a point is defined by the stress components acting on the sides of a differential element differential volume element, you write. that encloses the point. Okay. So if you take any standard textbook for this chapter called stress transformation, so you'll get this famous
show
picture.
that?
Which one? This one?
Yes.
Right first. Done?
Yes. Yes, done.
Now, what you do? You try to take the picture of this. Just a second. So I made this picture before. Just a second. Sorry, wait a minute. So I made that picture already. No, not this one. Yeah. So take this. So this is the standard state of stress. Okay. If you take any textbook, you will see something like this. So this is your sigma yy. This is tau xy. This is sigma xx. Draw this. So as of now, your state of stress at a point. So please remember, we are talking about a point. So there is a specimen. We are not talking about the specimen. You are taking a small point or a small differential element inside the specimen. Then you are analyzing. If you are able to find out for a point, you can do it for the specimen. You have to add up simply. Okay. So every time if you see any analysis in strength of materials, it's all about the differential element. Not only in strength of materials, you take fluid mechanics, solid mechanics, whatever it may be. You will try to take a small element, then you will try to derive some formulas using that. Then you will apply for the real applications. Okay, that's how it can be done. First, try to draw this, everyone. Are you done with this, guys? Can I continue?
Yes.
Okay. You write a body. The body may be subjected to stresses in one plane or in different planes these are always mutually perpendicular planes along with stress, or you write stresses at wait a minute, you write not at stresses at certain point can be resolved completely into stresses normal to those planes these planes which passes right these planes which passes through a point in such a way that the resultant across them is totally a normal stress are known as principal planes. Please underline this. So there are some planes where only normal stress will be there. There won't be any shear stress. So those kind of planes, we'll call those as principal planes. And the normal stress across these planes are called principal stress. So this is the maximum stress we are going to target. Underline this also. Write this. If I went too fast, take your time and write. Am I going too fast, guys? You want me to slow it down?
No.
No? Are you okay with this pace?
Yes.
Okay. Done?
Yes.
Just a second. Right, next one. The stresses acting on shear planes are maximum. I'll prove this, okay? Just wait for the derivation, then I'll prove this. Maximum shear stress and average normal stress. And remember, the normal stress on shear plane is not zero, okay? If you are thinking so. Even though there won't be any shear stress on a principal plane, it is not vice versa in shear plane. Okay, remember that. And there exists an average normal stress. I hope average means you understood. What do you mean by average? Guys, please underline this entire thing. That is sigma xx plus sigma yy by 2. Okay, that is your average. You're right. So when I am talking average stress in this entire chapter, it is this parameter. Sigma xx plus sigma yy by 2. Bracket this. So this is the average stress.